Good? All right, perfect. Okay, so just because there's not a reference on this video, I'm going to go ahead and say it one more time. We're working from the book, page 352. All right, so these are all the examples that you're actually going to need. So if you watch this whole video all the way through, all the numbers that we're going to do from the book are already on this slide. So you might actually see it in the video at some point or another. Actually, let me go ahead and flip through them if you want it from the video. There's this one, this, and you can pause the video and read through these if you want. And that's it. That's all we're doing today. Okay. Now, from this section, you're going to do 3. From this section, you're going to do 3. You're only going to need to do one of these, and then you're going to do each one of the applications. Okay, so here we go. The concepts we're actually learning today are actually very simple. It's really providing kind of a foundation for exponential functions. Later, we're going to start using logs, because in the same way that a square root, so for example, if I have like y equals, or let's not use y, let's say if I have 16 equals x squared, one of the ways I solve that, right, is by doing the square root, and a square root would undo the square, right? So you'd get x equals plus or minus the square root of 16, or plus or minus 4 would be your answer. So in the same way that a square root undoes a square, okay, a log is what undoes and solves for an exponential, all right, a variable in the exponent area. You don't know how to use logs yet. So today, at the end of your actual application problems, you see the word estimate, right? Because you don't know how to use logs. So you're not going to be getting an exact answer. You're going to be estimating your answer, okay? And then maybe tomorrow, maybe not tomorrow, in the next few days, somewhere in there, I'm going to insert the idea of logarithms, okay? And logarithms are how you solve for exponentials. Okay, so let's keep going with this. All right, so starting off, this is what you're doing in the first section. You're just simply evaluating, which means just to give me the answer, give me the value, all right, for these things when x equals -2 and when x equals 3. So I'm going to go ahead and do number 8, and you can pick any one of the 3 other ones that you want to do. I did all the evens up here. All the answers for the evens are up here, so you can check those if you want. All right, so if I'm evaluating, I'm going to get 2 answers at -2. Also, 2 to the at 3. Those are going to be my 2 answers. So this one, remember, 2 to the -2 is the same thing as what?
1 over 2 squared.
Yeah, so it's the same thing as 1 over 2 squared minus 2. So that's the same thing as saying 1 over 2 squared minus 2 is 1 over 2 squared is 4 minus 2. So you can have 1/4, which is 0.25 minus 2, which is going to be -1.75. Or maybe you want to keep it in fraction form, so you give that a common denominator, right? So you end up getting like 8 over 4. So 1 over 4 minus 8 over 4. So you could write it like this, -7 over 4, if you want to keep it fraction form, okay? So that's all I'm looking for that half the answer when x is -2. When x is 3, you have 2 to the 3rd, which is just 2 times 2 times 2, which is 8, and then minus 2. So 8 minus 2 is going to be 6. And that's that first section. It really is that simple. Okay. Any questions on the first section, guys? You understand what we're trying to do there? Okay. Section number 2. And all these things, every single section, very easy concepts. But they're new concepts, first of all. Second of all, there might be 3 or so of them, 3 or 4 concepts that you're trying to learn, all right? So they're all easy, but I understand if you don't understand one of them, okay, or something like that. So if you have a question, make sure you ask it. Chances are you're not going to understand one of these concepts. Okay, so next section. You're going to be choosing any 3 of these that you want to do. Tell me a number that you want me to do.
18.
Number 18. That was quick. All right. What I'm supposed to be doing is tell whether the function represents exponential growth or exponential decay. So guys, remember, an exponential function is the type of function where you're multiplying something over and over and over and over again, right? By some value. So if I'm multiplying on number 18 by 1.8, and and I multiply by 1.8, and I multiply by 1.8, is it going to be getting bigger or smaller? Bigger. So that's exponential growth when it's getting bigger and bigger and bigger. Exponential growth. Okay? So it says tell whether the function represents exponential growth or decay. This is growth. And it really is this easy. Watch. When I multiply by a fraction over and over and over, so I'm getting a fraction of the original over and over and over, should it be getting bigger or smaller?
Smaller.
Smaller. Okay, so this is going to be exponential decay. That's decay. That's decay. That's growth. Right? That's growth. That's decay. That's tricky. That's what that is. Right? That's 4 over 3, which is like approximately 1.3 continued. That's growth. Does that make sense? Even though it looks like a fraction, it should make sense to you guys. Y'all are all smart enough to get that. Okay? 1.2, that's growth. That's decay.
What if it's like 1?
If it's 1, is when I multiply by 1 times 1 times 1 times 1 times 1 times 1, right? And I keep multiplying by 1, is it changing at all? So is it growing? Is it decaying? It's not even, I don't even think it's just the same. It's not grow or decay. I was tempted to say I don't even think it's exponential, but I don't know. I don't know. It's not growth or decay, and it's pointless too. So for example, here we go. The most difficult question of the day. Are you ready?
Yes.
36 times 1 to the 675,292.61 power.
36.
The answer is 36. So it doesn't matter, right? It's not growth or decay. It's just, it doesn't even matter, right? It ceases to matter. I would even argue maybe that it ceases to be an exponential function because you're just taking 1 and multiplying it over and over and over. Okay. Any questions on this section? Oh, and then it says graph it. Sorry. Then graph the function. Okay, so remember I talked about all exponential functions, and this is all I'm looking for. I'm looking for a quick sketch. It's an exponential growth, so it's going to look like this. Okay? If it were exponential decay, just a quick example over here. If it were exponential decay, it would look like this. And it would decrease as x gets bigger, right? And increase as x gets smaller. Okay, y'all follow that? So this one is an exponential growth, so it's not decay. So you'll use that sort of graph on anything that's a decimal being multiplied over by itself. But all exponentials, right, generally speaking, go through this point. What point is that? It's when x is 0, anything to the 0 power is 1. So it's going through 0, 1. Okay? Y'all good with that? And also it goes through this point, which is going to be 1 comma, and in this case, if x is 1, what is my base? If x is 1, what's 1.8 to the 1 power? First power. It's just 1.8. So if an exponential at x equals 1, it should be the same as the base. So for example, this one's going to go through 1 comma 0.75. This one's going to go through 1 comma 2/5 or 0.4, right? This one's going to go through 1 comma 4/3. This one's going to go through 1 comma 0.6. Does that make sense? So that's all you need for this graph. That's all I'm looking for. All right. Make sure you don't cross over the x-axis, showing that you know there's an asymptote there. Any questions on the graphing, or whether it's exponential growth or decay? Good on those? All right. So same thing here now. It's just kind of a reverse order. It just says use this graph to identify what the base is. Okay, well, you should be able to identify the base when x is 1. Okay, so if I'm doing number 20, so you guys are going to do number 19 in a second. If I'm doing number 20, and I would like you to maybe write it in this format right here. When x is to the first power, what is the base? 5. So I should have really 5 to the x power. And let's just kind of make sure that makes sense too, because if x were 0, what's 5 to the 0 power? 1. And if x were negative 1, what's 5? 5 to the negative 1 should equal 1/5, right? So yeah, it works out. This is the basics of exponentials right now. Are we good there? Okay. Now, a few things I want to point out with this. Let's just work one of these examples, maybe fully together. Sure. Yeah, let's do it fully together. the value of a mountain bike, y in dollars, okay, can be approximated. So again, we're approximating also by the model y equals 200 times 0.75 to the t, where t is the number of years since the bike was new, right? So t is talking about how old the bike is. Now, what's the 200 representing?
Initial value.
Yeah, that's how much it costs now when t equals 0. So if you don't believe that, then figure it out. Now would be when t is 0, right? No time has passed. So what's 0.75 to the 0 power? It's just 1. And what's 1 times 200? So the value of the bike now, right, is 200. Okay, that's so the 200 is representing the current value of the bike. Now, what is this saying? Well, let's just read through the problem. We might actually get to these problems or these answers as we go through. So tell whether the model represents exponential growth or exponential decay. So is the bike losing value or increasing value? It's losing value. So it's exponential decay. And I would actually want you to write exponential decay out. Identify the annual percent increase or decrease in the value of the bike. So if it's exponential decay, it should be an annual decrease, right, in the value of the bike. Now, how much does it decrease?
25.
Yeah, that's it. I heard both answers, okay? So a lot of people would say 75%, but that's not how much it's decreasing. That's how much value the bike still maintains after every year, right? 75%, oh no, that stinks. All right, but the bike maintains 75% of its original value, right, every year, or previous value. Does that make sense? So it's decreasing 25% every year in value. Does that make sense? Okay, so identify the annual percent increase or decrease. It's a 25% decrease. It maintains 75% of its value. Right, so it decreases, it loses 25% of its value. All right, estimate when the value of the bike will be $50. Okay, so right now, because we don't know logarithms, if we wanted to, I could tell you exactly when it's going to be $50, okay, if I wanted. But right now, you don't know how to use logs, so we're just going to estimate. And the way that you could do that is say, all right, well, we want to find out when the value is 50. So the value is 200, starting with 200, and then you multiply by 75% every year. So the way I'd really do that is I'd say, well, how many years does it take for the 200 to turn into 50? So I'd start off like this, 200 times 0.75. That's the first year. What's 200 times 0.75? Does anybody know that off the top of their head? You can type it in the calculator, that's fine.
It's
150, right? Is that at $50 yet? No. Okay, that's year 1. Well, year 2 would be times 0.75 again. What's 75% of 150 now? Right? What's 200 times 75% times 75%? 112? 0.5, so it's not 50, so do it one more time, Dan. Just multiply by 0.75 again. So this is going to be 3 years at least so far.
84.37.
Not yet. So again, and this is exactly how I would do it right now. If I were in y'all's shoes, not knowing how to apply logarithms, right? I'll show you how to do logs in a second. So what's the fourth time?
63.28.
So we're getting close. Maybe a fifth time. One more time. 47. Okay, I'm going to say 47 is closer than 56. Okay, so I'm going to say approximately 5 years, right? It says estimate. So my answer, I could say about 5 years. 1, 2, 3, 4, 5. So look, just so you guys understand what an exponential is doing, when I write this like this is the same thing. Watch, 200 times 0.75 5 times, right? Does that make sense? That's the same thing. So I'm taking 200, and 1 year later, it's 75% of its value. Then the next year, I multiply whatever that was by 75% of its value, times 75%, times 75%, right? And that's eventually going to dwindle that $200 value down to $50-ish. So my answer, I could say, I could say about 5 years. I could say, what are some other good words? Roughly 5 years, approximately 5 years, right? However you want to say that. Okay, you guys good with that? I think that's about it. Everything else are all versions of that. So this is another great example. I'm going to ask you one question about B. I'm not going to write down the answer, but I want you guys to answer for me. Identify the annual percent increase or decrease in population. So based on my percent, is it increasing or decreasing? It's getting bigger, right? Not very fast, right? It's only increasing by how much? Just 3%, right? Because that's 100%. That's the original value. Then this how much is being added onto it every t, whatever t is representing. So it's increasing by 3%. Okay. With that being said, I think that is it.